a communication through free space, in the sense the atmosphere, right? There is no wire connecting transmitter and receiver, and we will be radiating signals, and then the receiver will be receiving the signals. So here comes the first step. So for radiating signals and then receiving signals, antenna called an antenna, which signals as inputs and then radiates electromagnetic waves. And similarly, receiving antenna, when electromagnetic waves impinge on that, on the antenna, then you will it will produce an electrical waveform at the output of the antenna, right? So that means antenna is an integral part of our our communication system. Now let us go back to one of the definitions. So let me just erase this down. We also did something. We also defined something called modulation, right? What did we define about modulation? If you go and see your notes, if you make any notes in the last class, that modulation is nothing but varying one of the parameters of a high frequency signal in accordance with the information signal to be transmitted. Right? So that meaning a high frequency signal will carry the information. Now let us start in this class. We will start with this model, and I'll introduce the concepts in this modulation. Modulation. So first, when we will in this modulation, as we are using a high frequency signal to carry a message signal. So why do we need to do that? So let us ask the question: why do we need to do modulation at all? Why don't we send the information signal as it is? Why do we need a carrier signal, and that too a high frequency carrier signal? We said that it is a high frequency carrier signal. So why do we need that? So so there are couple of reasons for that, but the prominent reason, the most compelling reason for doing this is the practicability of the antennas. So let me write that down in the sense. Okay, so in modulation, what we were doing in modulation is we were translating a low frequency signal to a high frequency range. So I'll make it clear what do I mean by this. But so okay, so what is the need for it? So the first need I was telling you is consider the antennas. Antenna size, right? So I don't know whether I think you have antennas course, but you will understand in antennas theory that an antenna effective size should be of the order of the wavelength of the frequency at which it operates. Right? So if you want to transmit a frequency, an electrical signal with frequency FC, then the size of the antenna for better operation of the antenna should be of the order of the wavelength corresponding to the frequency FC. Say, for example, what is the relation between wavelength and frequency? So wavelength lambda is equal to c by f, right? C is the velocity with which EM wave propagates through free space, right? And here we are talking about propagation in the free space, right? So C is, what is the value of C? 3 into 10 power 8 meters per second, right? And F is our frequency at which we want to operate the antenna, and lambda is its wavelength. So let us compute lambda for the information signals. So what information signal should we consider first? So let's consider the speech signal. Generally the Yep. So let me go back to the next page. Okay. So here let us see. So speech signal is from 0.3 kilohertz to 3.4 kilohertz. This is the spectrum over which the speech signals will be occupying. Like it is 0.3 kilohertz to 3.4 kilohertz. So just for simplicity's sake, let us consider we want to transmit. Say we want to transmit these speech signals as it is without doing any modulation or without using any high frequency carriers, right? So let us compute the lambda, the wavelength of the signal at these frequencies, because that wavelength will tell us the approximate dimensions of the antenna that we need to radiate these signals into the space. So just to make our numerical computation simpler, let us consider F is equal to 4 kilohertz. See, you can as well consider 3.4 kilohertz, but just to make our life simple, that's it. So in such a scenario, lambda is 3 into 10 power 8. Right, this is 4 kilohertz. So this is what? 55. Right, so your wavelength at this frequency is 75 kilohertz. And your antenna is as I'm not discussing the antenna dimensions and all here, as you will be studying that in your separate course, but it's generally are radius of a parabolic dish antenna or whatever different antennas which you will study. It's if the lambda is 75 kilometers, the effective dimensions of the antenna will be 7.5 kilometers. Like just imagine 7.5 kilometers dimension antenna, right? So which is impractical to have. Just so this gives us antenna dimensions will be of the order of 7.5 kilometers, right? Which is useless. In making through physics use. So now, it's not used. We have this to we have used a carrier frequency. So we will denote carrier frequency by F suffix C. C stands for carrier. So let us consider 1 gigahertz. So we are radiating these signals. So you will know how to translate and all that, right? Just now assume that now you want to transmit a signal at 1 gigahertz frequency. Then corresponding lambda will be So C by 1 gigahertz, 1 into 10 power 9. So that will be how much? 0.3 meters. Yeah. So you can do this calculation. C is 3 into 10 power 8 and divided by 10. Yeah, it is 0.3 meters. So your antenna size will be just 0.3 meters if you operate at 1 gigahertz, which is quite affordable, right? Like, so this is one of the main reasons of going to a high frequency range for transmitting signals. Generally, these signals occupy the low frequency ranges, at least audio. Audio is from approximately 50, and speech it's from, yeah, you can say, right? So let me change the page, right? So let us just to give you some interesting thing, like say right now in 5G wireless. So right now, if you are using these mobile phones, it is from 8 4G. The G, we are using fourth generation mobile technology, and soon in another 5 to 10 years you will be using 5G, fifth generation mobile technology. So in that they are planning to operate at approximately 30 gigahertz. So your carrier frequency will be like we will be transmitting at 30 gigahertz. So at this frequency, what is the wavelength? So you can compute this much smaller, and then because the wavelength is so small, you can devices can also become smaller, but you have other problems when you go for higher frequencies. You will learn that in your electromagnetic wave propagation and such subjects, like your attenuation will be very high, right? Yeah. So yeah, so one of our main motivation is at higher frequencies we can use antennas with smaller dimensions. Right? That's one of our motivation. Yeah, as a just as a host, you to think about this, like, right? So okay, this is all about communication through free space over the air. Like it is also called over the air because we are transmitting into the air, and it's the only way communication happens. There is also something called underwater communications. Like how do you communicate underwater? Like two submarines, how do they communicate? Or if you are marine life, like if you are doing marine archaeology or whatever. So if you want to communicate underwater communications, operating at low frequencies preferred, not at higher frequencies. So just think about it. Why it, right? So see, this may not be in your curriculum, and I'm sure this may not be a question for your exams, but just think about it. Like, so I'm just trying to write this out. Sorry. So in underwater, in the water you can communicate through acoustic waves, optical, and also RF. So let me not confuse you with all those things. In underwater communications, we prefer using low frequency. frequencies. So just try to guess the reason, right? Okay, just discuss with your friends or with your faculty members, whatever. One and two hints I can give you is one is, yeah, okay, let's okay, you think about it, we can discuss it later, right? Okay, so yeah, so let me change the page again. Yeah, so one of the reasons. Sorry. Reasons for frequency translation. So what do I mean by frequency translation? We are moving from low frequencies to high frequencies. That meaning if we want to transmit a signal, our so I have to. So am I audible now? Hello. Hello.
Yes, sir.
Yeah. Okay.
Hello?
Yeah.
Yes, sir.
So yeah. Okay. I'm starting. Yeah, so I hope you are able to see 0.3 kilohertz to 3.4 kilohertz. We'll be in this course, we'll be mainly talking about translating that to 300 kilohertz to 3000 kilohertz, which is medium frequency range. And this is where all our amplitude modulation systems work, right? So this is the place for amplitude modulation. Hertz to 300 megahertz, very high frequency, and this is where we use frequency modulation. So we'll again revisit these frequency ranges, and the entire course is about what is AM and what is FM, right? Okay. So this is so one of the main reasons that we discussed was the practicability of the antenna dimensions, right? So now there are that's though that is the primary reason, there are also other reasons which require us to do this frequency translation from a lower frequency range, to the higher frequency range, right? So let us quickly discuss those three aspects. So the other reasons, So why I put two is the first one is practicability of the antennas, and the second one is kind of multiplexing different signals. So the second reason is multiplexing. So what do I mean by multiplexing? So let us see what does it mean, right? So say for example there are two users, both of them are producing speech signals, and they want to communicate over the same channel meaning same free space channel, right? So the user one is producing his signals within the range zero point 0.3 to this right, 0.3 kilohertz to 3.4 kilohertz, and this other user is also generating signals in this range. But if these two signals are transmitted over the air, like over the free space, then they will interfere with each other heavily. So the one, so let's so one possibility is you say that there are U1 and U2. So U1 is also generating 0.3 to 3.4 kilohertz, and U2 is also generating the same signals. So let us now translate that to say, for example, the first user signals, you translate that to some frequency range F1 to F2, and this second user signals you translate that to another frequency range F3 to F4. Say F1 to F2 and F3 to F4. Right? So if these two frequency ranges are non-overlapping in frequency, then they don't interfere with each other. Right? You understood? Okay, let's do one simple example. So we are still discussing multiplexing, right? There is a signal. Yes, let's call this as minus F1. This is plus F1. Right? Say this is F low. This is FH, and this is signal 1. So how do I call it? Say maybe V1 of F. So this is there is a message signal V1 of T, and we are computing its Fourier transform. So this signal is occupying this signal is occupying a spectrum minus F1 to plus F1, right? And say there is another user who is trying to communicate, and his spectrum is something like this. Say his is F2, obviously it's minus F2, and this is plus F2. Again, see this FL and FH, why I am writing? I'm just trying to indicate to you that they are in the same frequency range. So this frequency range FL to FH remains same, but in the same frequency range, we want to transmit one signal having its spectrum like this, and we want to transmit another signal having its spectrum like this. Right? Say this, we call it V2. V2 of F. The frequency, the magnitude of the frequency spectrum of the second signal. So as I was just saying, if I send these two signals as it is without any frequency translation, right? So they interfere with each other. And so what does frequency translation do? So let us do the frequency translation of these two signals. So when we do this, it will be something like this. So right? So, well, so this is the first signal. This is the second signal. So this is FC1, and what is that point? FC1 minus F1, and this point is FC1 plus F1, right? And say this is FC2, and this is FC2 minus F2, and this point is FC2 plus F2, right? So this is a frequency axis. This is the frequency axis, right? So we have two signals here. We have two signals here. One is V1F, another is V2F in the frequency domain. And then they are occupying the same frequency range. But if we transmit them as it is, of course, one difficulty is the antenna. So even forgetting about the antenna difficulty, if we transmit them as it is, they interfere with each other. So say for example, this is what we do in wireline telephone communications. In wireline telephone communications, you know there is no need of antenna, right? When you speak over your landline phone, your signals goes through the copper cable, like the wire line, right? Up conversion, frequency translation. But even there, you do this kind of frequency translation because all of us speak, all of our speech is in the same range, 0.3 kilohertz to 3.4 kilohertz. Right. So to differentiate signals from different users, we move the frequency of one user into some using one carrier. So this is the frequency range occupied. So this is the frequency range occupied by user 1, right? This is for user 1 signal, and similarly for user 2, this is the frequency range occupied. Right, this is U2. Yeah. So this is called frequency division multiplexing. You will be studying also time division multiplexing in your digital communications. So yeah, okay, let me emphasize that this is called frequency division multiplexing because you are multiplexing different signals in the frequency domain. You are translating them to different domains and then multiplexing them out. So this is called frequency division. Yeah, let me write that. So I'm moving to the another page. So this is frequency division multiplexing. You cannot do similarly, just as in frequency division, we can also do time division multiplexing, as I was saying, but you will study that later. Okay, so now let's go to the third reason. So first reason was antenna size. Second reason was if the message signals of two or more users occupy the same frequency spectrum, then they interfere with each other. So we need to separate them. To separate them in the frequency range, we will use frequency translation. So what about the, sorry, it should not be, yeah, so it should be 4, right? Just a minute. Okay. Frequency. Oh, okay, sorry. So that's 2, and yeah, I'm sorry, this 3 only. So first one is antenna, second one is multiplexing, and third one is So if you think about perfect English, this narrow banding term doesn't seem to be a correct word from the point of English, but technically it makes sense. So let us see what it is. So narrow banding is, say for example, I was telling you that speech occupies from zero point 0.3 kilohertz to 3.4 kilohertz, right? And okay, just now for another example, consider audio signals. So audio signals occupy, say, this is approximately, so 50 hertz to 10 power 4 hertz. So 10 power 4 hertz is 10 kilohertz, right? Okay. So now let's think about transmitting these signals, transmitting an audio signal, which could be occupying, which can lie anywhere in this frequency range. Say some of the audio signals may be just around 100 hertz, and some of the audio signals may be around 10 kilohertz, right? So what is the ratio of f max by f min? So f max by f min. What do I mean f max? F max is maximum frequency, the upper end of the frequency range. Say yeah, so we are considering transmitting some audio signals which can occupy range from 50 hertz to 10 kilohertz. So the maximum at any given time, the maximum frequency that we will be transmitting is 10 power 4 hertz, and the minimum frequency that we will be transmitting is 50 hertz. And what is the ratio? It is 200, as you can see readily, right? So that meaning your lambda max by lambda min is also ratio of 200, right or wrong, right? See, your wavelength ratio is also 200. Like some of the signals correspond to wavelength of lambda max. Some of the signals correspond to wavelength of lambda min in this frequency range. Then the antenna, if you design with respect to, okay, assume that even you can design an antenna at this frequency, or at this frequency, you try to deploy that, even forgetting the practicality reasons, right? Then the antenna which designed based on this is very inefficient to transmit these signals, and the antenna which is designed based on this is very inefficient to transmit these signals. So what I mean to say is the dynamic range, the range of f max to f min or lambda max to lambda min is so high that it leads to many practical difficulties. So now let us consider translating this frequency to a carrier frequency of how much should we say? So let me take this example from the notes. So maybe 1 megahertz, or yeah. So let us see this. Consider translating this to 1 gigahertz. Okay. So maybe it's simpler if you take 10 power 6 hertz. So 1 megahertz, right? So then if you simply compute f max by f min, so if you translate this with a carrier frequency of 10 power 6 megahertz, your max will be 10 power 6 plus 10 power 4 hertz divided by 10 power 6 plus 50 hertz. So this approximately is 1.01, right? So you understood why do we get this? Because here you have seen that if this occupies from minus f1 to plus f1, if I translate that using a carrier frequency of fc1, my new spectrum will be fc1 plus f1 or fc1 minus f1, right? So this is my new maximum frequency, and this is my new minimum frequency. This is my original maximum frequency, this is my original minimum frequency, right? So that's how we got this. So now the maximum frequency to minimum frequency ratio is almost equal to 1, right? So in that sense, this is called a narrow band signal. So what is a wide band signal and what is a narrow band signal? If I don't know, maybe you would have studied in your signals and systems, but a narrow band signal is defined as with respect to its center frequency, the bandwidth is much smaller, right? So let me write that down. In a narrowband signal with respect to its center frequency, the BW stands for bandwidth. The bandwidth is small. So here, what is the center frequency for us? 10 power 6. And what is the bandwidth? 10 power 4 Hz minus 50 Hz is the bandwidth. So it's approximately, you can say 10 power 4 Hz. So the bandwidth is smaller compared to the center frequency. So that and previously so that's how we changed a wideband signal which is from 50 Hz to 10 power 4 Hz to a narrowband signal. So this purpose of narrowbanding is also possible with frequency translation, right? So I hope this is clear. Like, so now we'll move to the next one, which is circuitry, the ease of circuitry or whatever. Say for example, the fourth reason is what should I say? Ease of, sorry, my writing, I have to practice with this. So that was processing. Ease of circuits or processing. So let us see quickly what this is. Say we want to process signals having similar characteristics but occupying widely different frequency ranges. Say we want to transmit signal, we want to process signals from 50 Hz to 10 kilohertz or from 1 megahertz to say we want to process signals of bandwidth W. Say either the W signals are between F1 to F2 or F3 to F4 or F5 to F6, right? So we prefer to use the same circuits. Then in that case, it's because it is advantageous if we convert those signals into a predefined band. So let me, okay, so what I do is, this is something called intermediate we will discuss this later. Later, in the sense, we will discuss this super heterodyne receiver. In that we will come across this term of intermediate frequency. So you will be able to appreciate more at that point of time. So for the time being, just take it granted. I know that I'm not explaining this in detail, but we'll discuss this more. We'll discuss later. At the time of so when we discuss the AM receiver, we will discuss this point in detail at that time, right? So primarily, what I want to say is there are four reasons for moving from one portion of the spectrum to another portion of the spectrum, right? So we are moving from speech range or audio range to a higher frequency, which is megahertz or gigahertz. So there are four reasons. So just to summarize, one is antenna size. Second one is what do we call multiplexing. Third one is narrowbanding. Like we want to make these signals as narrowband signals so that the dynamic frequency range is not that high. And fourth one is ease of processing. Right? This we'll discuss later. So let us add a star mark to that. Right? Yeah. So now having established the why we need to translate in frequency, why we need to move from say some frequency range f1 to f2 to a higher frequency range. So let us start discussing about how can we do it. Right? Okay, so we thought that moving to a higher frequency range is advantageous, but now we should think about how do we do this practically and such things. So let us move to the next topic, which is how to achieve frequency translation. Right. So in this, let us quickly recall the Fourier transforms. We'll make use of, sorry. Yeah, I hope you all remember your last semester course on signals and systems, which you did. I think you must have spent a lot of time on Fourier transforms. Uh, yeah, so let us quickly recall that. Say consider there is a signal. So let me change the page so that. Yeah. Yeah. Where should we start? That v of t can be expressed as, or yeah, it's Fourier transform v of f. This is its Fourier transform, and we call v of t and v of f, or yeah, so let me write this v of f to e power j2 pi of t v of t e power minus j2 pi of t dt. So and we call it, so I'm not going into the basics of Fourier transform, as that is not the intention of this course. As I said in the last class, we assume that I asked you to refresh these basics. So but the notation, just for the sake of notation and all, I am trying to do this. So v of t Fourier transform pair is denoted like this, right? So if v of f is the Fourier transform of v of t, or v of t is the inverse Fourier transform of v of f, we will write them like this. So this is the notation we follow. Like, so here sometimes some people use ft, but no need. Like if there are multiple transforms we are considering, we can use either it is Laplace transform or Fourier transform or whatever. But we will be dealing with Fourier transforms in this class. So yeah. Yeah, so with this background, let us think we have a signal. We have a signal Vm of t. Say consider consider a message signal. Vm of t is some am cos 2 pi fm of t. Right? There is a message signal, a sinusoidal message signal, or cosine signal, right? Whatever. So this, we know that a message signal is not a strictly sinusoidal or cosine signal, right? But just for ease of exposition, like just to start with, what is this frequency translation? So think about this, and let us say we want to translate this to a frequency fc. Then a simple way of doing this translation is to multiply these two signals together mathematically, and another signal frequency fc. Say, let me write vc of t, carrier signal is ac cos 2 pi fc of t. So we'll see that through Fourier transform analysis, through mathematics, that multiplying these two signals will translate this signal at fm to a frequency at fc. And here we also assume that fc is much higher than fm. Yeah, or fc is simply higher than fm. Right. So let us see. Or yeah. So maybe here. Yeah. Okay, so this I can write this as am by 2 e power j 2 pi fmt plus e power minus j right. So e power j theta plus e power minus j theta. Oh, yeah. Please excuse me. I have to connect the laptop charger. So let's break. Just 1 minute. Give me 1 minute. 2 e power j 2 pi fct plus e power j 2 pi fct. So there is a minus sign here, right? Yeah. Yeah. So now let us assume we were multiplying these two signals, right? So what is our claim is, if we multiply this Vm of t with Vc of t, we will get the frequency translation. Let us see whether it happens or not. Okay. So let's okay before. So and let us see Vm of f. Okay, so what I'm trying to say is Vm of f. What is the frequency? Sorry, Fourier transform of. So this is Fourier transform of am by 2 e power j 2 pi fmt plus e power minus j 2 pi fmt, right? So the Fourier transform of Vm of t is this. So what is this? Am by 2. What is the Fourier transform of this? Yeah, anyway, I don't have chart window to get your feedback, but we'll fix that up in your next class. But so I hope you remember this. So this is delta f minus fm, and this is plus delta f plus fm. right? So a complex exponential, the Fourier transform of a complex exponential e power j 2 pi fm is an impulse in the frequency domain. So this is what I said in the last class when I asked you to prepare or refresh your knowledge about signals and systems. I expect you to go and read the Fourier transforms at least, right? If you haven't done, there is no problem. You can study at least now. Like you should see how this derivation comes. You should revisit. So what does it mean? So what we are making use of Fourier transform of e power j 2 pi fmt is delta of f minus fm. So just do this. Check this as homework, right? Yeah. And now how does this spectrum looks like? Say this is 0 and this is f. So we have two impulses, one at fm, one at minus fm. So this is fm minus fm. And what is this height? Am by 2. So what is the y-axis? It's the magnitude of Vm of f, right? So yeah, so there is no space for me to write that here, but it is magnitude of Vm of f. Yeah. So this is the spectrum. Oh, sorry. Spectrum of Vm of t. Yep. So now similarly, let's do this. So it's straightforward. Uh, so I will directly write the equation. So what will be the spectrum of Vc of f? Well, Vc of t. So Vc is a frequency at Fc, right? If I change simply M to C, it will be AC by 2 and e power j 2 pi Fc, so and so on. So let me do that quickly in the next page. So similarly, Vc of f will be AC by 2 into delta f minus Fc plus delta f plus Fc. You should also check this out, right? And its frequency, and as remember we said it is Fc is much higher than Fm, right? Say this is 0 and we said this is Fm. This is minus Fc. This plus Fc. So this is amplitude, and the amplitude of both these impulses are Am by 2, and the amplitude of both these impulses is AC by 2 and AC by 2, right? Yeah. So this is I just plotted the spectrum of both the signals on the same diagram. That's it. Now let's quickly consider what happens when we multiply. So multiply Vm of t with Vc of t. So what do we get? Am by 2, Ac by 2, and then we are multiplying what? E power j 2 pi fmt plus e power minus j 2 pi fmt, that is getting multiplied with e power j 2 pi fct plus e power minus j 2 pi fct, right? So there will be 4 terms in the resultant expression, and those 4 terms we'll just write it on the next page, right? So this may be fairly simple, but I'm just doing it so that you won't have any confusion. So Vm of t into Vc of t is equal to Ac Am by 4, right? Into we'll have e power j 2 pi Fm plus Fc of t plus e power minus j Fm plus, sorry, into 2 pi. I forgot the 2 pi there. So this is 2 pi Fm plus Fc into t plus e power j 2 pi Fc minus Fmt plus e power 2 pi Fc plus Fmt. Right. So you just verify this and then find its Fourier transform now. So what is the Fourier transform? Okay, having done this multiplication, Fourier transform of Vm of t, Vm of t into Vc of t is equal to, I hope you are getting these things right. Like this is, yeah, there is an impulse. Okay, you can see that there is an impulse at epsilon fm, there is an impulse at minus fc plus fm, right? And there is an impulse at fc minus fm, and there is an impulse at minus of fc plus fm, right? So you, just as a homework, you can complete this out. Like you find Fourier transform of each of this term. We already know that Fourier transform of a e power j 2 pi fm is delta function at fm, right? And then right. So I'm just directly writing the spectrum here, like say directly drawing the spectrum here. So let us see how it goes. Like so I'm changing the page. Now after multiplication, what do we have? So here we have 0. And so here we have 4 terms in the Fourier transform, right? Like of the fc, and similarly this minus fc. the frequency. Now we have Fc minus, so there is an impulse here. There is an impulse here. So this is Fc minus Fm. This is Fc plus Fm. Right. So similarly, there will be an impulse here. Yeah, maybe I should put them of the same size, all the impulses. So what is the amplitude of these impulses? It is AM AC by 4. So similarly here, so this is minus Fc minus Fm minus Fc plus F. Right, there will be 4 times. That's what, if you see, there is Fm plus Fc, all corresponding to all these 4 terms. You will have four delta functions here, and then pictorially, that is this. You will be having this. Right. So in this spectrum, you don't have anything around Fm. Right. There is nothing called Fm here. There is no impulse in the original spectrum of message signal. Is there is an impulse at Fm here, and there is an impulse Fm here. But now we have this frequency, this Fm got translated into a frequency Fc minus Fm and Fc plus Fm. So this shows us that simply multiplying 2 signals ensure in frequency domain, like ensure us through Fourier transforms that we can translate the spectrum, right? So I hope you got convinced that multiplying 2 signals will do the task for us. Will shift the frequency, will translate the frequency range from some low frequency to high frequency. Yeah. So now this is for a single sinusoidal. If you go back and see, what we considered was we considered only this Vm. Yeah, sorry. So we consider simply this V of t. Yeah, sorry. Yeah, so we consider a sinusoidal message signal Vm of t. But now let us consider a message signal which occupies a certain frequency range. See this. What is Vm of t? Vm of t is just one sinusoid. So in frequency spectrum, it has got only one frequency component. But a speech signal or audio signal will have so many frequency components. It has got a finite bandwidth. So what is it to do with Vm of t? Vm of t bandwidth is 0, right? If somebody asks you either in a Viva or somewhere, what is the bandwidth of Vm of t? It has got no bandwidth, in the sense it's a pure sinusoid or it's a pure cosine signal, just a delta function at Fm. But yeah, just something like this. But when we speak, the speech signals vary in the frequency from 0.3 to 3.4 kilohertz, or any signal, or take a video signal. It will have a finite bandwidth from F1 to F2. So what happens if we so our original intention was to take a message signal occupying a finite bandwidth F1 to F2 and then move it to a higher frequency in the frequency spectrum. So now let's consider that whether the same operation can do this or not. So our intuition says that yes, we can do this. If we can do this for single sinusoid, we can do this for any finite bandwidth signals. But let us do that both graphically and through mathematics. and convince ourselves that yes, this technique works, and then we will go on to discuss more about. So yeah, give me a second. So I want to conclude here that multiplying two signals effectively can perform frequency translation. Now, yeah, let us consider a message signal. Having non-zero bandwidth. Right? So yeah, so let's consider some message signal m of t having its Fourier transform m of f. Right? So what is m of f? M of t into e power minus j 2 pi ft dt. Right? So this integration is over minus infinity to plus infinity and so on. So right. So now let us consider multiplying m of t with AC cos 2 pi fct. Right? So m of t into, that means I can write this as AC by 2 into e power j 2 pi fct plus e power minus j 2 pi fct. Right? This is the multiplication. Correct? Then this is equivalent to AC by 2 m of t e power j 2 pi fct plus m of t e power minus j 2 pi fct. Correct. Now let's take Fourier transform of this. Okay. So if you, yeah, so take Fourier transform of m of t of e power j 2 pi fct. So basically what I'm trying to do is I'm trying to take Fourier transform of this and take Fourier transform of this. Right? Fourier transform is a linear operation. So Fourier transform of a plus b is Fourier transform of a plus Fourier transform of b. Right. So now what is this? So this is m of t e power j 2 pi fct multiplied by e j 2 pi ft dt. Right? So this is the signal we want to take Fourier transform. That signal multiplied by e power minus j2 by ft dt. So this is equivalent to, yeah, this is from minus infinity to plus infinity. I am missing that most of the time, but please take care of it. So this is m of t e power j2 pi minus fc dt. Right. So now what is this? This is, see, we know that, just go back and see. We know that, see here, this equation, m of t into e power minus j2 pi ft dt is m of f. Right? The Fourier transform m of f is equivalent to m of t multiplied by e power minus j2 pi ft dt. Now, in our expression, we have, in place of f, we have f minus fc. Right? See here, we have f minus fc. So simply, this is nothing but m of f minus fc. That means the Fourier transform shifted by an amount fc. Right? So similarly, you will get Fourier transform of m of t e power minus j2 pi fct. Sorry, just a minute. Yeah, so this is equivalent to, you can show that so what do I mean that is, so what do we understand is that by multiplying a signal m of t with AC cos 2 pi fct, will shift its Fourier transform centered at fc and minus fc. That's it. So let's do this pictorially. Let's see the graphical representation. Right? So I said m of t is a finite bandwidth signal, right? So let me write its. So this is magnitude of Fourier transform of the message signal. So let this be something like this. So this is the FM minus FM is the frequency. See, this is the spectrum of the message signal. The message signal is occupying, I assume that it has a finite bandwidth signal having bandwidth of FM, right? It has maximum frequency of FM. And when I do this spectrum, I assume that the spectrum is symmetric with respect to the origin. So why do I assume that? Okay, so I hope you remember the properties of the Fourier transform. So if what is the time domain characteristics of a signal whose frequency spectrum is symmetric with respect to this zero frequency? It's a conjugate symmetry property, right? So it's a conjugate symmetry property, and so let me give you the answer. You should again go and check this out, like so. So m of t is a real valued signal because it's is symmetric with respect to, so this is with respect to so you have to verify this by going back to your Fourier transform material, right? Yeah. So now let's come back to the task at hand. So this is we have a signal m of t having a spectrum like this, and then we are multiplying that with a carrier signal, a cos 2 pi fct, and let us say the carrier signal frequency is here, is fc. So similarly, this is minus fc, right? So after multiplying, what do we get? What do we get is, say, this is fc, so this is fc minus fm, this is fc plus fm. Similarly, we have so this is minus fc, this is minus fc plus fm, minus fc. Of course, the magnitude, sorry, the magnitude should get reduced, right? Say if this is the, yeah, you should, this magnitude should be, what did I say? M of t, say let's consider m of t magnitude is 1, and then magnitude of cos 2 fct is AC, then it would be AC by 2. This magnitude would be AC by 2, assuming m of t has unit magnitude. That meaning this is 1, right? So we just checked that even with a finite bandwidth signal, we can achieve the frequency translation by multiplying with a sinusoidal signal of a higher frequency, right? So with this, we'll kind of stop. Like, so what we will do is, now our task is, mathematically we know that, okay, let me, yeah. So our task is, mathematically we know that we can, by multiplying with a signal, we will